Okay, well, welcome back to our class on software engineering. We're continuing in our section here on advanced software engineering. We just finished up talking about systems engineering. And so in this lecture, we're going to be going to another related topic per se. We'll be talking about, sorry about that. We'll be talking about systems of systems. And so this complements pretty well what we've already covered. But there's another aspect of this that's important to be looking at, and that we're not just doing things in isolation. A lot of times you have to be considering that that context. And so when we talk about system complexity, system of systems classification, reductionism and complex systems, system of system engineering, and systems of systems architecture. For a system of systems, more and more systems are being constructed by integrating existing independent systems. A lot of things are deployed and they're working great. And so you're just trying to stitch those together and there's a new application that you can create. So a system of systems is a system that contains two or more independently managed systems. There's no single manager for all the parts of the system of systems, and the different parts of the system are subject to different management and control policies and rules. So what are some examples? You can have a cloud management system that has local private cloud management and management of services on public clouds such as Amazon and Microsoft. You can have online banking that handles loan requests, which connects to a credit reference system provided by a credit reference agency to check the credit of an applicant. And for emergency information systems, you can have things that integrate information for police, ambulance, fire, and Coast Guard services about the assets availability to do with civil emergencies such as flooding and large-scale accidents. So what are some of the essential characteristics of a system of systems? There's operation independence of system elements. There's a managerial independence of system elements. There's evolutionary development, emergence of system characteristics, geographical distribution of system elements, and data intensive and heterogeneity that would be found in this. For complexity, all systems are composed of parts or elements with relationships between these elements of systems. For example, the parts of a program may be objects, and part of each objects may be constants, variables, and methods. The complexity of any system depends on the number and types of relationships between system elements. The type of relationships, static or dynamic, also influences the overall complexity of a system. Here are just some illustrations of systems and different ways how they may be architected and the type of complexity that they have. So A just sort of shows more of a hierarchical approach, and system B shows a lot higher connectivity between the elements. For process complexity, as systems grow in sizes, they need more complex production and management processes. Complex processes are themselves complex systems. They're difficult to understand and may have undesirable emergent properties. They are more time-consuming than simple processes, and they require more documentation and coordination between people and the organizations involved in the system development. The complexity of production processes is one of the main reasons why projects go wrong with software delivered late and over budget. So here is an illustration of system production and management processes. And so you have the production process. And so it's like that, you have the management, and those feed into these things. And so as a result, that you have the production process produces, the management process manages, and you have this complex system that's illustrated on the bottom. So what about complexity and software engineering? Complexity is important for software engineering because it is a main influence on the understandability and the changeability of a system. The more complex a system, the more difficult it is to understand and to analyze. As complexities increase, there are more and more relationships between the elements of the system, and an increased likelihood that changing one part of a system will have an undesirable effect elsewhere. What are the types of complexity? You can have technical complexity, managerial complexity, and governance complexity. For technical complexity, it is derived from the relationships between the different components of the system itself. For managerial complexity, is derived from the complexity of the relationships between the system and its managers and the relationship between the managers of different parts of the system. For governance, complexity of a system depends on the relationship between the laws, regulations, and policies that affect the systems and the relationships between the decision-making processes in the organization's responsibility for the system. Here is a chart showing the system characteristics and complexity. So operational independence, managerial independence, evolutionary development, emergence, geographical distribution, data intensive, and heterogeneity. And so you can see most of these show a correlation between technical complexity. A handful have managerial complexity, and a different set have governance complexity that would have to be considered. What about complexity and project failure? Large-scale systems of systems are now unimaginably complex entities that cannot be understood or analyzed as a whole. The large number of interactions between the parts and the dynamic nature of these interactions means that conventional engineering approaches do not work well for complex systems. It is complexity that is the root cause of problems in projects to develop large software intensive systems, not poor management or technical failings. What about systems of system classifications? And so here are several classifications. You can have a direct system of systems. These are owned by a single organization or developed by integrating systems that are also owned by that organization. The system elements may be independently managed by parts of the organization. There's collaboratives, a system of systems. These are systems where there's no central authority to set the management priorities and resolve disputes. Typically, elements of the system are owned and governed by different organizations. And finally, virtual systems, where they have no central governance and the participants may not agree on the overall purpose of the system. Participant systems may enter or leave the system of systems. Well, let's talk about more in intuitive classification terms. You can have organizational system of systems, federated systems, and system of systems coalitions. For organizational systems of systems, these are systems where the governance and management of the systems lies within the same organization or company. For federated systems, these are a system of systems where the governance and of the system of system depends on the voluntary participation body, participative body in which all the system owners are represented. And system of system coalitions are a system of systems where there are no formal governance mechanism, but where the organizations involved informally collaborate and manage their own systems to maintain the system as a whole. Here is comparison of system of system classifications. And so you have the organizational versus federation versus coalition. So governance, they do have elements in both the organizational and federated and nothing in the coalition. And beyond that, we see some similar ways things are done in the technical and managerial. You can see different ways of how that would play out. What about the iLearn system that we've periodically brought up in the course as a system of system? iLearn is a relatively simple technical system, but it has a high level of governance complexity. The development of a digital learning system is a national initiative, but to create a digital learning environment, it has to be integrated with network management and school administrative systems. There's no common governance process across authorities. So according to the classification scheme, this is a coalition of systems. Okay, let's get into reductionism and complex systems. For complexity management and engineering, the approach that has been the basis of complexity management and software engineering is called reductionism. Reductionism is based on the assumption that any system is made up of parts or subsystems. It assumes that the behavior and properties of the system as a whole can be understood and predicted by understanding the individual parts and the relationships between these parts. To design a system, the parts making up the system are identified, constructed separately, and then assembled into the complete system. For software engineering methods, a reductionist approach has been the basis of software engineering for almost 50 years. Top-down design is where you start with a very high-level model of the system and break this down to its components in a reductionist approach. For reductionist methods are successful when they are relatively few relationships between the parts of a system, and it is possible to model these relationships. Software engineering methods attempt to limit complexity by controlling the relationships between parts of a system. Reductionism does not work well when there are many relationships in a system and when these relationships are difficult to understand and analyze. For reductionist assumptions, system ownership and control, reductionism assumes that there is a controlling of the authority for a system that can resolve disputes and make high-level technical decisions. Rational decision-making, reductionism assumes that the interaction between components can be objectively assessed, for example, mathematical modeling. And finally, for defined system boundaries, reductionism assumes that the boundaries of the system can be agreed and defined. Here's an illustration showing a system of systems reality. This gets into control, decision-making, and problem definition. And so you can see the reductionist assumptions that they see it in a different way versus what is the reality of the system of systems and how it actually is. So in terms of reductionism and software system of systems, relationships in software systems are not governed by physical laws. Political factors are usually the driver. Software has no physical limitation, hence there are no limits on where the boundaries of system are drawn. The boundaries and the scope of the system are likely to change during its development. Linking software systems from different owners is relatively easy since we are more likely to try and create a system where there is no single governing body. Okay, let's talk about system of systems engineering. So what are some of the problems with system of system engineering? There can be a lack of control over system functionality and performance. There can be differing and incompatible assumptions made by the developers of the different systems. Different evolutionary strategies and timetables for the different systems can exist, and there can be a lack of support from system owners when problems arise. Here's an illustration of a system of system engineering flow. And so you have the systems knowledge that flows into the conceptual design, which is going to be impacting the system selection and getting involved in architectural design. Governance and management policy setting also will be things that will be considered. And so as you're trying to work towards your interface and integration and deployment, these are things that will come up. For conceptual design, this is the activity of creating a high-level vision for the system. For system selection, this is where a set of systems for inclusion in the SOS is chosen. And the architectural design is where an overall architecture for the system of system is developed. For the interface development, this is the development of a systems interface so that the constituent systems can interoperate. For integration and deployment, this is making the different systems involved in this system of systems work together and operate through the development interface. And system deployment means putting the system into place in the organization's concerns and making it operational. For interface development, the aim of a system of system development is for the system to be able to communicate directly with each other without user intervention. So for service interfaces, if systems in a system of system have service interfaces, they can communicate directly via these interfaces. The constituent systems in a system of system often have their own specialized API or only allow the functionality to be accessed through their user interfaces. You therefore have to develop software that recognize the differences between these interfaces. For service interface development, to develop service-based interfaces, you have to examine the functionality of the existing system and define a set of services to reflect that functionality. The services are implemented either by calls to the underlying system APIs or by mimicking user interactions with the system. A principal system acts as a service broker, directing service calls between the different systems in the system of systems. Each system, therefore, does not need to know which other system is providing a service call. Here is an illustration of the service interfaces. The various services are integrated into the interface that people would access, and then you have the principal system. For a unified user interface, the user interfaces is for each system, and the system are likely to be different. A principal system must have some overall user interfaces that handles users' authentication and provides access to the features of the underlying system. It is usually expensive and time-consuming to implement a unified user interface to replace the individual interfaces of the underlying system. So what are the cost effectiveness of a user interface development? There's the interaction and assumption of the systems in the SOS. There's a mode of use of the SOS, and there's a quote openness of the SOS, and these are all have to be considered. For integration and deployment for SOS, it makes sense to consider integration and deployment to be part of the same process. Separate integration may be difficult as some of the systems in the SOS may already be in use. The integration process should begin with systems that are already deployed, with new systems added to the SOS to provide coherent additions to the functionality of the overall system. For stage deployment of the iLearn system, the initial deployment provides authentication, basic learning functionality, and integration with school administrative systems. Stage 2 would add integrated storage and a set of more specialized tools for subject-specific learning, and stage 3 adds features for user configuration and the ability for users to add new systems to the iLearn environment. And then you could continue with various releases. So maybe you start some basic functionality with Office programs, Office 365, for example, conferencing system, authentication systems, and then you begin adding some additional things with each release. For testing, SOS testing, there are 3 reasons why testing of a system is difficult. There may not be a detailed requirement specification that can be used for a basis for system testing. The constituent systems may change in the course of the testing process. And if problems are discovered, it may not be possible to fix the problems by requiring one of the or more of the constituent systems to change. For SOS testing and agile testing, agile methods do not rely on having a complete system specification for system acceptance. Stakeholders are engaged with the testing process and decide when the overall system is acceptable. For SOS, a range of stakeholders should be involved in the testing process if possible, and they can comment on whether or not the system is ready for deployment. Agile methods make extensive use of automated testing. This makes it much easier to rerun tests to discover if unexpected system changes have caused problems for the SOS as a whole. Okay, well, let's talk about system of systems architecture. There's a variety of general architecting principles to consider. Design systems so they can deliver value. If they are incomplete, be realistic about what can be controlled. Focus on the interfaces, the system interfaces. Provide collaborative incentives. Design a SOS as a node and web architecture. Specify behavior as services exchange between nodes, and understand and manage systems vulnerabilities. For an architectural frameworks such as MODEF and TOGAF have been suggested as a means to support the architectural design of systems. An architectural framework recognizes that a single model of an architecture does not present all of the information needed for architectural and business analysis. Frameworks propose a number of architectural views that should be created and maintained to describe and document enterprise systems. TODAF is a framework that has been developed by the Open Group as an open standard. It is intended to support the design of a business architecture, a data architecture, an application architecture, and a technology architecture for an enterprise. At its heart is the architecture development method, ADM, which consists of a number of discrete phases. Here's just a picture showing the architectural development method for TOGAF, and I'm just gonna, you can look over that at your leisure. For architectural model management, initial model development takes a long time and involves extensive negotiation between system stakeholders. This slows the development of the overall system. It is a time-consuming and expensive to maintain model consistency as changes are made to the organization and the constituent systems in a SOS. For architectural patterns for SOS, an architectural patterns is a stylized architecture that can be recognized across a range of different systems. Architectural patterns are a useful way of stimulating discussions about the most appropriate architecture for a system and for documenting it and explaining the architectures used. For systems as data feeds, there is a principal system that requires data of different type. This data is available from other systems, and the principal system queries these systems to get the data required. Generally, the systems that provide data do not interact with each other. This pattern is often observed in organizational or federated systems where some governance mechanisms are in place. Here is an illustration of systems as data feeds, and you can have a number of feeds that feed into principal systems, and that's the data that is used. So as system as data feeds, the systems as data feeds, quote, architecture is an appropriate architecture to use when it is possible to identify entities in a unique way and create relatively simple queries about these entities. A variant of the systems as data feed architecture arises when there are not a number of systems involved which provide similar data which are not identical. The architecture has to include an intermediate layer to translate the general query from the principal system into the specific query required by the individual information systems. So here is an illustration of the systems as data feeds with unifying interfaces. And so you can see that different things have to be brought together and put into the right formats is what we're trying to illustrate. For a system as a container are systems of systems, or one of the systems acts as a virtual container, provides a set of common services such as an authentication and a storage service. Conceptually, other systems are then placed into the container to make their functionality accessible to the system users. You don't place systems into a real container to implement the system of systems. Rather, for each approved system, there is a separate interface that allows it to be integrated with the common services. Here's an illustration of a container system. And so you can see how that potentially could be constructed. For the iLearn container, you can be thinking about the common services. And so there's an authentication service for a single sign-in to all approved systems. You can have a storage service for user data. This can be a seamlessly transferred to and from approved systems, and a configuration service that is used to include or remove systems from the container. And here is a illustration of iLearn as a container. And so you have these various things that you bring into that environment, whether it be YouTube or encyclopedia, different office type of applications, simulations, analyzers, and all of that is fit into the main components of what's in the learning environment. What are some of the container architectural problems? A separate interface must be developed for each approved system so the common services can be used with these systems. This means that only a relatively small number of approved systems can be supported. The owners of the container systems have no influence on the functionality and behavior of the excluded systems. Systems may stop working or may be withdrawn at any time, and that can be a real concern. Well, let's think about training systems. Training systems are systems of systems where there's no single principal system, but processes may take place in any of the constituent systems. The systems involve trading information among themselves. There may be a one-to-one or one-to-many interaction between these systems. Each system publishes its own interface, but there may not be any interface standard that are followed by the systems. So here is just an illustration of how these trading systems can communicate with one another. For trading SOS, trading systems may be developed for any type of marketplace, with the information exchange being information about the goods being traded and their prices. While trading systems are systems in their own right and could conceivably be used for individual trading, they're most useful in an automated trading context where the systems negotiate directly with each other. The major problem with this type of system is that there is no governance mechanism, so any of the systems involved may change at any time. Okay, well, let's finish up with a handful of charts with key points. Systems of systems are systems where two or more of the constituent systems are independently managed and governed. There are three types of complexity that are important to systems of systems: technical complexity, managerial complexity, and governance complexity. System of system governance can be used as the basis for a classification scheme for SOSs. That leads to the three classes of SOS, namely organizational systems, federation systems, and system coalitions. Reductionism as an engineering method breaks down because of the inherent complexities of systems. Reductionism assumes clear system boundaries, rational decision-making, and well-defined problems. None of these are true for systems of systems. The key stages of the SOS development process are conceptual design, system selection, architectural design, interface development, and integration and deployment. Governance and management policies must be designed in parallel with these activities. And finishing up, architectural patterns for system of systems are a means of describing and discussing typical architectures for SOSs. Important patterns are systems as data feeds, systems in a container, and trading systems. Okay, with that, we'll finish up this lecture. Thank you very much.